In this video, we discuss the PAC-Bayesian bound. This generalization bound helps determine whether a deep neural network will overfit the training data or not. Given the extremely large number of parameters in deep neural networks, over-parameterization occurs. In this context, we cannot rely on traditional machine learning viewpoints, which propose that models with a large number of parameters are more likely to overfit. Here's the outline of this presentation. First, we introduce the PAC-Bayesian learning framework. This framework works by averaging a group of models to learn. Next, we explore the PAC-Bayesian bound in detail and explain its underlying intuition. This bound reflects how parameter changes during training influence the generalization ability of a learning algorithm. Finally, we compare the PAC-Bayesian bound with the VC bound in the context of neural networks. The VC bound is a common generalization bound used in traditional machine learning analysis. However, the VC bound depends on the number of parameters in a model and, as a result, typically predicts overfitting for neural networks. In contrast, the PAC-Bayesian bound does not heavily depend on the number of parameters. Hence, it is a more accurate tool for determining whether a deep neural network will overfit the training data. First, we'll cover some preliminary concepts for the PAC-Bayesian learning framework. We begin by introducing the concept of a stochastic model, which is commonly used in the PAC-Bayesian framework. In a deterministic model, the model consists of a single hypothesis H. The error of this hypothesis, denoted as epsilon h, is calculated by evaluating h on a data set. In contrast, a stochastic model consists of a distribution of hypotheses, denoted by q. To evaluate the stochastic model on a dataset, a hypothesis h is randomly sampled from q. The error of this sampled hypothesis is epsilon h. The error of the entire model, epsilon q, is the expected value of epsilon h over the distribution q. In this section, we explain the process of training stochastic models. The model prior to training is referred to as the prior, represented by P, which describes the distribution of hypotheses before any training takes place. Next, the training algorithm uses the training data to modify the hypothesis distribution. Once the training is complete, the modified hypothesis distribution is known as the posterior, represented by Q. This procedure is analogous to Bayesian inference. In Bayesian inference, the prior P is the distribution of hypotheses before observing the training data, while the posterior Q is the distribution after observing the training data. Let's delve deeper into the training process. The training phase resembles the process of training a deterministic model. A set of training data is drawn from the data distribution. However, in this case, the model represents not a single hypothesis, but a distribution of hypotheses. Thus, the training error is assessed by computing the expected error epsilon hat q across this distribution of hypotheses. Once the training error is determined, a training algorithm is developed to minimize it. This algorithm updates the hypothesis distribution, typically by adjusting the parameters that govern this distribution, which in turn leads to a reduction in the expected training error. Once the model has been trained, since the training algorithm has only observed the samples in the training data, it is necessary to evaluate the trained model using the original dataset. A subset of data is selected as the testing dataset. The trained model is then evaluated on this dataset, where the testing error, denoted as epsilon q, represents the expected error across the distribution of trained hypotheses. To show the feasibility of learning within the PAC-Bayesian framework, McAllister's work demonstrates a generalization bound. If we can show that a small training error, denoted by epsilon hat q, implies a small testing error, denoted by epsilon q, then learning becomes feasible. The PAC-Bayesian bound provides a probabilistic guarantee with a confidence level of 1 minus delta that the following inequality holds. On the left-hand side is the testing error epsilon q, while the right-hand side consists of epsilon hat q plus an additional term involving a square root. This additional term is referred to as the generalization gap, which quantifies the difference between the training error and the testing error. If the generalization gap is small, the testing error is likely to be small when the training error is also small, with high probability. Now, let's examine the generalization gap in more detail. The KL divergence between P and Q appears in the numerator, representing the difference between the prior and posterior distributions. A small KL divergence implies a small generalization gap, indicating that overfitting is less likely to occur if the model's distribution does not change significantly during the training process. In the denominator, n represents the number of training instances. This implies that as the size of the training dataset increases, the likelihood of overfitting decreases. Here we present the intuition behind the generalization bound. We use solid dots to represent training instances and hollow dots to represent testing instances. At the beginning of training, the algorithm adjusts the hypothesis distribution only slightly, so the KL divergence between P and Q remains small. Because the distribution Q is still far from fitting the training data, the training error is high. Since the KL divergence is small, the PAC-Bayesian bound suggests that the gap between the training error and the testing error will also be small. Thus, the testing error is similarly high, which reflects a state of underfitting. As training progresses, the distance between P and Q grows, leading to a larger KL divergence. At the same time, the training error decreases due to further optimization. In this case, a larger KL divergence in the PAC-Bayesian bound implies a greater difference between the training and testing errors. However, the decrease in training error dominates, resulting in a lower testing error. If the KL divergence remains moderate, not too large, the testing error will also be moderate, as the generalization gap remains small. This reflects the case of appropriate fitting. On the other hand, if excessive training is performed, Q will begin to overfit the training data. Consequently, the KL divergence between P and Q becomes very large. The PAC-Bayesian bound indicates that this large KL divergence will cause a significant gap between the training error and the testing error. Despite the very low training error, the large generalization gap will lead to a high testing error, which is characteristic of overfitting. Here we highlight an important characteristic of the PAC-Bayesian bound: it is data-dependent. This is crucial because in deep learning applications, overfitting is often caused by the data distribution rather than the number of model parameters. Let's consider two examples. In the first, the data consists of blue and orange dots with a clear boundary separating them. Even if the model has high complexity and can create very intricate boundaries to fit the training data, it doesn't need to adjust much during the training phase to capture this separation. As a result, the KL divergence between P and Q remains small, which leads to a smaller generalization gap and minimizes overfitting. In contrast, when the data is noisy, the model must undergo significant adjustments to fit the noisy boundaries in the training data. This leads to a large KL divergence between P and Q, resulting in a large generalization gap and severe overfitting. Jugeit's work presents an experiment comparing the PAC-Bayesian bound with the VC bound in a neural network setting. In this experiment, the MNIST dataset is modified into a binary classification task, where class 0 includes digits 0 through 4 and class 1 includes digits 5 through 9. This modification simplifies calculating the exact generalization bound in binary classification scenarios. The experiment is conducted in 3 settings. In the first setting, 2 neural networks with different hidden layer widths, 600 and 1200 units, are compared. The results show that increasing the hidden layer width has no effect on the training or testing errors. The VC bound, which is related to the number of parameters, doubles due to the increase in hidden layer width. However, no overfitting occurs, consistent with the PAC-Bayesian bound, whose generalization gap remains stable. This suggests that even though the number of parameters doubles, the model doesn't need much adjustment to fit the training data. Thus, the PAC-Bayesian bound only increases slightly. The second experiment explores the effect of increasing the number of hidden layers. The results are similar to the first experiment. That is, the VC bound increases fourfold, yet no overfitting occurs, still consistent with the PAC-Bayesian bound. The third experiment involves randomizing the labels, introducing noise. In this case, the training error is low because the neural network's complexity allows it to memorize the training data. However, the testing error rises to its maximum, indicating severe overfitting. In this scenario, the VC bound remains unchanged since it does not depend on the data distribution. Meanwhile, the PAC-Bayesian bound increases significantly and aligns with the observed overfitting. This occurs because the model undergoes major adjustments to fit the noisy data, resulting in a high KL divergence in the PAC-Bayesian bound. This experiment shows that the PAC-Bayesian bound can explain overfitting in neural networks, whereas the VC bound cannot. Here is the key takeaway. First, the generalization gap predicted by the PAC-Bayesian bound reflects the change in parameter distribution during training, which leads to the increase of generalization gap. Since this distribution change depends on the data distribution, the PAC-Bayesian bound can explain when overfitting in deep learning is likely to occur. However, traditional machine learning theory, such as the VC bound, only considers the number of parameters in a model, and therefore cannot explain why deep learning models do not always overfit. Thus, to prevent overfitting in deep learning, it is more effective to reduce noise through data cleaning and establish a more robust data collection pipeline to improve label consistency. On the other hand, reducing the number of parameters is ineffective for mitigating overfitting in deep learning scenarios. Here are the references. The first reference is the original paper on the PAC-Bayesian bound, which includes a comprehensive derivation of the bound. The second reference is a paper that applies the PAC-Bayesian bound to neural network settings and conducts experiments comparing it with the VC bound. This paper provides both theoretical insights and experimental details regarding the application of the PAC-Bayesian bound to neural networks. Thank you for your listening.